Now let's define stress at a point. So we want to find the stress from the traction. Earlier we have seen from the forces. Okay, from the force we find the traction, that is intensity of force. Okay, now given traction, how can we find the stress? So it is very easy. No, the how to get the stress components. So stress components are estimated by finding the traction, okay, on three perpendicular planes. So traction is a vector. We know it has three components resolved into three XYZ axis. Okay, so T1, T2, T3. So finding this traction on three different planes or three perpendicular planes. Okay. So let's understand this how it is happened. Okay. So let's take this coordinate system here, XYZ, and this is our body. And let's assume that we have already defined a traction here at a point in this on this body. Okay, and this traction is Tn. So we know traction is always associated with reference plane, which is described by normal n. So this is a traction Tn, and as we know it's a vector, so it has three components. Okay, T1, T2, T3. So we can write in tensorial form something like this: T1, T2, and T3. Okay, now this traction is given. Okay, now at this point we want to find the stress. Okay, so what is the stress at given point where traction is known? Okay, so as we said, no, finding the traction on three different planes, that's how we get the stress components. Okay, so let's define no, if we want to find the stress, we need to define infinitesimal volume here, right? So let me draw it larger. Okay, this is our infinitesimal volume around that point. Okay, and this is a point. Let's know first find the traction T1 on three different planes. So T1 is there, which is aligned with x-axis. So let's now focus only on x component of traction, that is T1. Okay, now yeah, I think I need to draw even bigger. Doesn't look in proportion. So this is our infinitesimal volume. Let's check, this is y-axis, this is our x-axis, and this is z-axis. Okay. So this traction, okay, let's take this is a T1. Now no, just assume, imagine that this traction T1, okay, it is exploded in volume. Okay, so we want to find the impact. Actually it's not proper technical word, but for understanding we can understand in this way, like we want to find the impact or impact of T1 on three planes, that is x, y, and z. Okay, so if I take the impact of this T1, okay, on x plane, okay, I get stress component. So sigma stress due to traction T1 on plane x. Okay, so sigma 1 1. So uh, again I repeat, the stress due to traction T1, the first indice due to traction T1 on plane x, okay, the second indice. So that is sigma 1 1. Now this this is a impact on x plane. Now similarly we can do it for y plane. So this just no, imagine like you are exploding this T1 on this plane, y plane, on this top plane. Okay, so I get sigma stress due to traction T1 on plane y. Okay, so sigma 1 2. So understand that first and second indice. Okay, that first indice is due to traction T1 and second indice is on a plane. Okay, so x and y. So similarly z plane, so this front plane is a z. So I will take find the component of T1 on z plane. Okay, so this is my stress due to traction T1 on plane Z. So sigma 1 3. Okay. So this is how you get three stress components. Okay. So we can say like one traction component. Okay. One traction component gives us three stress components. Okay. So sigma 1 1, sigma 1 2, and sigma 1 3 due to T1. And we can also put no, we can also find sigma 1 1 here. Okay, so that it is in equilibrium. So it is actually on three six faces. Okay, so sigma 1 1 on this face and sigma 1 1 on this face. Okay, so for an equilibrium. Similarly sigma 1 2, okay, on this plane we can get sigma 1 2 in this direction. So due to equilibrium, uh, the point should be in equilibrium, right? Or infinitesimal volume should be in equilibrium. So sigma 1 1 on this side and opposite side in opposite direction. But we get a three stress component. One traction component gives us three stress components. Okay, so now we will be able to understand like how stress is second order tensor. So earlier we have discussed about tensor, right? So matrix is a second order tensor and we have given example of stress and strain as a second order tensor. So second order tensor means it requires three dimensions to define that tensor. So one is magnitude, then direction and associated plane. So this is a tensor. And now we can see like for if you want to define the stress, okay, the stress magnitude is given this sigma 1 1. Its direction is the first indice is in sigma 1 1, the first indice 1 is direction and its associated plane is second indices. Okay, so to define this stress, the magnitude, and there are this one is for direction, this one is for associated plane. So that's how the stress is second order tensor. Now that we have found the stress components due to T1, okay, similarly the same way we can also find the components of T2, okay, on three different plates, and there also we get three stress components. Okay, we can draw in similar fashion. Okay, but for a T2. Okay, so this is our infinitesimal cube volume. So T2 here at this point, this is a T2. So the T2 on three different planes. So let's take first on X plane, the finding the T2 component on X plane. Okay, so in this direction we get the stress here. So stress due to T2 on X plane. Okay, similarly this is a stress due to T2 on Y plane, sigma 2 2. Okay. And here as well on Z plane, the stress due to T2 on plane 3, plane Z, okay, sigma 2 3. So that's how we get this three stress components on three different planes due to T1. Now similarly, T3, okay, the traction component in Z direction, we also get three other stress components. So I can quickly draw this. So this is a T3 in Z direction. Okay. So finding the T3 component on X plane, we get this stress. Okay, sigma due to T3 on plane 1, sigma 3 1. Okay, on Y plane, sigma 3 2. Similarly, on Z plane, stress due to T3 on plane Z, sigma 3 3. Okay, so this also gives us three stress components. So let's combine all these uh, stress components. Okay, so these three stress components due to T1, these three stress components due to T2 and T3. Okay, if we combine them all, we get nine stress components, right? So here from this sigma 1 1, sigma 1 1, sigma 1 2, sigma 1 3. Okay, then due to T2, sigma 2 1, sigma 2 2, and sigma 2 3. Similarly, due to T3, so sigma 3 1, sigma 3 2, sigma 3 3. Okay, so this is how we get stress components at a point. So this is called stress at a point. It is also called stress state. And if you observe this, okay, the T1 gives us three stress components, in which one is normal stress component, okay, that is sigma 1 1, and we get two shear stress component, okay, sigma 1 2 and sigma 1 3. Okay. Similarly, here we have one normal and two shear, one normal stress and two shear stress components. Okay, so stress as at a point we have three normal stresses. They are sigma 1 1, sigma 2 2, and sigma 3 3. Okay, and six shear stress components. So sigma 1 2, 1 3, 2 3, 3 2, sigma 1 3, and sigma 3 1. Okay, but no, this sigma 1 2 and 2 1 are equal. Okay, we are not going to prove it, but rotational equilibrium, from a rotational equilibrium we can show that sigma 1 2 is equal to 2 1, sigma 2 3 is equal to sigma 3 2, and sigma 1 3 is equal to sigma 3 1. Okay, that means sigma ij is equal to sigma ji, where I is not equal to j. So shear stress components. So this how we get three normal stresses and three shear stresses, because due to rotational equilibrium, six shear stresses will boil down to three shear stresses. Okay. So let me now summarize, okay, the stress at a point, or how we can write stress at a point or describe the stress at a point. Okay, in tensor form or in matrix form. Okay, so sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3. Okay, this is a stress at a point. Okay, this is in matrix form. In tensorial notation, we can write it as sigma ij. Okay, where I is a direction of stress, and j is associated plane. And we can also say sigma ij is equal to sigma ji. Okay, and these these three components, okay, they are the stress components coming from T1 traction, right? This is from T2, and these are from T3. Or if we say column wise, these three components are acting on plane 1, right? Plane 1 or plane X. These three stress components are acting on plane 2, okay, or Y plane, and these three stress components are acting on plane 3. So this is the overall picture of stress at a point. Okay, it's very simple. Okay, the first notation indices is direction of stress. The second indices is associated plane on which stress is acting. Okay, so let's understand this normal stress components and shear stress components. Okay, very quick introduction. So the normal stress components, okay, they result in tension or compression. That means no stretching or compression. So we can also say stretching or compression. So if I want to show it on particular structure, let's say this structure, simple structure, okay, and let's take this is a plane here. So the normal stresses are acting on this plane. So the normal stresses always act normal to the plane, okay, and they result in stretching or compression. This is stretching. So these no normal stress components are like kind of a push or pull nature, and shear stress components, okay, they result in sliding, okay, shearing or sliding. Okay. So let's understand with similar structure. Okay, if this structure, okay, let's say this is the plane, this is our plane. So the shear stresses act in plane, okay, it's not normal to plane, so they act in plane, and they result in sliding. So hope this is clear.